Okay, we're on lesson 8.2, area in the plane. So far we've done area as an integral, and it is really the area trapped between the curve and the x-axis. What we were doing before was really treating the x-axis as y equals 0. So if your function is above y equals 0, then your area is going to be positive because you have your function minus 0. If your function is below the x-axis, then the top function becomes y equals 0, and you're subtracting the bottom function of where your original equation is. Then that equation, that area is going to be negative. So two things you want to remember from this lesson is that if your function, one is on top, one is on the bottom, to find the area between these two regions, you take the top minus the bottom. If your function is graphed as an x equal function, so it is a sideways function like in number 2 here, then you want to go with the idea of the right minus the left. So you want to make sure you go with two things. You want to remind yourself that it's either top minus bottom or right minus left. Okay, so let's go ahead and take a look. If you can, I would suggest to color code what you see here. Unfortunately, for some reason, my colors aren't matching up too nicely, but what I want to remind you of is that you want to use one color for a top function and another color for the bottom function. That way, when you're looking at it, it's a little bit easier to see what is the region we are really dealing with, okay? So ideally, something like this, you will have you have the calculator to kind of help you. But this first function, 1/2 secant squared t, is this blue function right here that's already graphed out for you, right? And the second function, the negative 4 sine squared t, is this green function that I've graphed down here. Okay. So my top function is the 1/2 secant squared t. My bottom function is negative 4 sine squared t. And then notice how the graphs don't intersect each other. So when they don't intersect each other, most of the time we'll give you an interval. We'll tell you, hey, we're going to start looking at negative pi over 3 all the way to pi over 3. So the region I'm looking at, the area I'm looking at, is this piece right here that is between the green and the blue function, the blue and the green function. And then your interval is going to trap the beginning and the end of it, right? So over a domain interval, you're doing the top minus the bottom, right? So top function minus the bottom function. Hence my setup is, as you see here, 1/2 secant squared t minus the negative 4 sine squared t, of course dt, right, over the region negative pi over 3 to pi over 3. So two things we can do here. First thing we can deal with is the fact that, hey, this is actually an even function. If you look at the area being trapped here, you have symmetry. So you don't have to do the entire integral. If you know that you have symmetry and the left side exactly the same as the right side, you can actually simplify this to be double. And instead of doing the whole thing, I'm just going to do half of it. I'm going to do it from 0 to pi over 3. That way, if I double the area, I get the whole thing, right? So 0 to pi over 3. Generally, I do that because I would prefer to not deal with a negative number. A lot of times plugging in negative numbers really does get a little bit confusing, a little bit more work, because you have to keep in mind the negative does change something. So whenever I can plug in 0 instead, I choose to go with that. Okay. First things first, I would clean this up a little bit with all the minuses and stuff. So 1/2 secant squared t plus 4 sine squared t dt. Okay, just looking ahead here and say, hey, well, I know what the integral of secant squared is. Secant squared integral of that is tangent t. But sine squared doesn't have something to work with. So this is where you got to recall your knowledge of some identities from trig. So the identity would be, this would have been the half angle identity, or it could be from double angle as well. So the double angle formula that you saw, right? So cosine of 2 theta back in the days was 1 minus 2 sine square theta, right? And there was another one, the other option was 1 plus 2 cosine square theta, right? So to get your sine square theta, you want to go ahead and solve this identity so you can substitute it in. So If I move things around, if I subtract a 1, I get cosine 2 theta minus 1 equals -2 sine square theta. If I divide by -2 on both sides, then sine square theta is equal to -1/2 cosine 2 theta plus 1/2. It's a lot easier to write it this way, and it's a lot easier to tackle it this way, because then when you're taking the antiderivative, notice now it is just a cosine 2 theta, not cosine square theta. So a single power cosine is a lot easier to take the antiderivative of than a trig function to a power, especially sine or cosine to a power. So what I'm going to do is I'm going to replace that. I get 1/2 secant squared t plus 4, and instead of sine squared t, I'm going to replace that with -1/2 cosine 2t plus 1/2. So really the goal of this lesson is not only to show you how to figure out the area between two functions, the top minus bottom or the right minus left, but also show you some of the tricks that you may encounter when you have different functions. Like in this case, we have to change it from an original sine squared to a double angle formula or double angle identity to make it so something that is something that you could take the integration of. Okay, so go ahead now. I'm going to clean up more. I'm not ready to take the antiderivative yet. Right, so I'm going to distribute the 4. I get -2 cosine 2t plus 2 and then dt. Okay, now I am ready. I can go ahead and take the antiderivative. I get, my 2 is on the outside still, 1/2 tangent of t, because the antiderivative of secant squared is tangent t, minus 2. The antiderivative cosine is positive sine of 2t, but there's chain rule. There's a 2t in there, so you got to take out a 2 for the reciprocal of the coefficient. And then you have 2t evaluated 0 to pi over 3. Okay, so then you have 2 half tangent of t minus sine of 2t plus 2t 0 to pi over 3. Okay, so now we're going to plug it in and evaluate 1/2 tangent of pi over 3 minus sine of 2 pi over 3 plus 2 pi over 3 minus, very lucky because sine of tangent of 0 is 0. Sine of 0 is still 0, plus 2 times 0 is 0, so the second parentheses is 0, so it's very nice. The only thing that you need to watch out for is cosine, but we don't have cosine here, so it's very good. Okay, so we get 2 times 1/2 tangent of pi over 3 is root 3 minus sine of 2 pi over 3. So 2 pi over 3 is in the second quadrant up that way, so it's root 3 over 2 plus 2 pi over 3. So then don't forget to distribute your 2. So you get root 3 minus root 3 plus 4 pi over 3. Final answer of 4 pi over 3 to be this area. You can put unit squared. If it doesn't ask you for the unit, you really don't have to care too much about it. But again, if you want to be really PC and very careful and watch out for everything, you can put unit squared here. It will be more essential that you put the units in once we are comfortable with this concept. Okay? All right. So now in this case, in the second problem here, it says x equals 12y squared minus 12y cubed. Again, this is something that either we will give you the graph of, or it will be something that is a little bit easier to do in terms of plugging in into the t-table. All right. So for now, in the interest of time, we are going to give you the function. This is the blue function. This is the blue one right here going this way, right? And then this is the green function. X equals 2y squared minus 2y. So this is the green function. So in this case, you are doing the right minus the left. There is an order to this. Top minus bottom. Top is usually positive, so positive minus negative. Same thing here. Right is usually positive on the x and y axis, so right minus left. The top minus bottom, right minus left. You know, you see this function here, it is naturally crossing at 0 to 1 on the y-axis. So therefore, notice how the interval is 0 to 1. This time I don't need to give you interval, but I did anyway. In the directions it did, so it tells you the range of 0 to 1. It doesn't always do that. Sometimes if it naturally does crossover, sometimes the directions will be very limited and just say, hey, find the the area between these two functions, and that will be the two functions where it cross naturally, and that will be your interval. All right. So be careful when you're subtracting your functions. Be careful to mark the fact that it's the top or the right function minus a left function. So make sure you put parentheses because the minus makes a big difference in your answer, right? And then for me, I am going to go ahead and remind myself that this is my green function. So not make it so red, okay? All right, now I'm ready to work this out. Before I take the integral, I always clean up my function first. I'm not sure why, but there are always students that just go ahead and take the interval and antiderivative, and it's just a lot of work if you don't clean this up. So 0 to 1, I'll put this in standard form, so highest power to lowest power. So negative 12y cubed, and then you have 12y squared minus 2y squared, so plus 10y squared, and then minus a negative 2y, so plus 2y dy. Okay, I am ready. So antiderivative, I get negative 12 y to the fourth over 4. So negative 3y to the fourth plus 10y cubed over 3 plus 2y squared over 2. So y squared, evaluated 0 to 1. And again, we should learn to really appreciate polynomial functions now, because a polynomial function, knowing that when you plug in a 0, you'll get 0. You don't have to worry about that second plug-in, right? So you get negative 3 times 1 plus 10 over 3 times 1 plus 1 minus 0. All right. So again, get comfortable with your fractions here. Negative 3 is negative 9 over 3 plus 10 over 3 plus 3 over 3. So 13 minus 9, your answer is 4/3 square units. All right, so that will be the area of this piece right here, this piece that's trapped between the right and the left function here. Okay. All right, sometimes the graph does intersect beautifully, but we want more than that. So in this case, you have your blue function here, which is the parabola, and then you have your green function here, which is the linear function. And I'm now asking you to look at from negative 2 to 3. So from negative 2 all the way to 3, notice how this area is actually in 3 pieces. So that's why you can see the work here. It starts out with the green, right? This is the green portion. This is the top function minus the bottom function. So my green function is on top. So that was my linear function minus the quadratic, right? And then the second piece here now, the top function is a parabola. So the top function minus the bottom function minus the linear function, negative x plus 2. And then once again, this last piece here, the top function is green and the bottom function is blue. So the top function is my linear function, negative x plus 2. And I'm going to use that to subtract the quadratic, right? And again, watch out for your interval, right? The first piece went from negative 2 to negative 1. So that's why my negative 2, negative 1. Second piece goes from negative 1 to 2. So negative 1 to 2. Last piece goes from 2 to 3. So my interval 2 to 3. Okay. So that they all have their pieces. And a good way to check is look at your picture here. I see 3 regions, therefore 3 integrals, right? 1 area per integral. Okay, now I'm ready to work this out. Once again, I strongly recommend to clean this up in terms of adding combining like terms before you start taking the antiderivative. Okay, so I get negative 2 to negative 1. Make sure I don't lose that. My highest power is x squared, so negative x squared, that's positive x squared, minus x, plus 2 minus 4, so minus 2 dx. All right, second integral should clean up nicely. I have negative x squared, got it, minus a negative x, so plus x, and then 4 minus 2, so positive 2 dx. And again, once they flip over, you can see my first integral, my second integral. When you look at the cleaned up version, the negatives just change around because you subtract the other one and vice versa, right? And then the last piece of interval will be 2 to 3, and then you get x squared minus x minus 2 dx. All right, now I'm ready to take the antiderivative. So you get x cubed over 3 minus x squared over 2 minus 2x, evaluated negative 2 to 1, plus negative x cubed over 3 plus x squared over 2 plus 2x, evaluated negative 1 to 2, and lastly, x cubed over 3 minus x squared over 2 minus 2x, evaluated 2 to 3. So, okay, so now you're ready to go ahead and plug in your interval. And so don't forget to really watch out for your signs and make sure that you combine like terms. You're gonna see as I'm writing these out, as I'm plugging them in, I don't try to reduce too much because I'm trying to save all the common denominator fractions so that I can go ahead and add them up all at the end. And that way that will make my answer a little bit easier to tackle, okay? All right. So your final answer should be 49/6. Okay, next. Now, sometimes the functions are a little bit more plain and straightforward. You have your two functions here. You have your 2x minus x squared, so that's your parabola. And then you have your linear function here, y equals -3. So based on this picture, you can see in my region that I'm covering, first of all, there is some natural crossings here. So we cross at -1 right here. We cross at 3, so that's your natural interval. And you can also see that you have a top function and a bottom function, so it's going to be a top minus bottom situation here. So your integral should be set up as your area is going to be top minus bottom. So it's going to be for your interval, you're looking at the cross at -1 to 3, top minus bottom, and it's dx. How do I know it's dx? First of all, your equation is going to be in terms of x values right here. See how it's 2x minus x squared. Secondly, your interval are along the x-axis. Therefore, this is a dx problem, okay? All right, your top function was 2x minus x squared. Your bottom function was a -3, okay? So now I'm going to clean this up before I go ahead and work this out. I get -1 to 3, highest power is -x squared, plus 2x, plus 3 dx. And now I'm ready to take the antiderivative of this function here. So -x cubed over 3 plus x squared plus 3x evaluated -1 to 3. All right, so plugging in the 3, I get -27/3 plus 9 minus -1 cubed. So that's negative and negative, so positive 1/3 plus 1 minus 3. All right, same thing we did in the previous problem. Go ahead and combine the same fractions, right? Same denominator, so that'll make it a little bit easier to work with. So I get -7 minus 1, so -28/3 plus 9, so that's 18. 18 minus 1 is 17 plus 3, so that's 20. So it's a little bit easier to work with. So I get -28/3 plus 60/3 because I change it to the same denominator. That will give me 32/3 as my final answer for my area. All right, next picture, very similarly, I have a parabola on top, so I can probably guess it's gonna be this one. But notice it's not written in the form I like, so you will need to spend a minute here to write it as y equal. So to make it y equal, it's gonna be y equals -4x squared plus 4. We're gonna write it as 4 minus 4x squared, no big deal, okay? And then the bottom function is this one right here. Same thing, you wanna rewrite it as a y equal function so we can actually use it. So this is going to be, if I add the y over and I move the 1 back, I get y equals x to the 4th minus 1. So then again, once again, this one has a very natural crossing at -1 to 1, right? -1 to 1. But I also noticed that, hey, this is an even function. So I actually don't have to go all the way from -1 to 1. I can just go down the middle and just do this half right here, right? So my setup could be very simple. Area is going to be double from 0 to 1. It's a lot easier that way. Top function minus the bottom function, dx. Again, we're looking at the x-axis, so it's dx. Top function is going to be the blue, -4x squared plus 4. Bottom function is going to be the green, x to the 4th minus 1. Okay, I'm going to clean this up. I get 2, 0 to 1. Highest power is going to be negative x to the fourth minus 4x squared. And then you have 4 minus a negative 1, so plus 1, plus 5 dx, right? So then you are ready to take your antiderivative, right? This one's going to be a little bit better to do. So you have negative x to the 5 over 5 minus 4x cubed over 3 plus 5x, evaluated 0 to 1. Now again, this is a polynomial function, so we know we don't need to spend time plugging in the 0. We're going to get 0. So it's just plug in the 1, negative 1/5 minus 4/3 plus 5, right? And again, if you need to, just show yourself that minus 0 there. Okay, now this is what I'm talking about. You have fractions, right? So you have 2 here. You can make it all a common denominator, or you can just add up the first 2 and then add the next 2, up to you. For me, I see it's 15. So negative 3 over 15 minus 20 over 15 plus 75 over 15. Okay, so I got 2. 75 minus 23, that would give me 52 over 15. And I will oh, sorry, it ran away. Go ahead and multiply this out. I get 104 over 15 square units. Okay, you're probably going to guess this is going to get uglier and uglier. So the answers are not going to be nice whole numbers. Start getting used to that, especially starting from this lesson and on. Okay. All right. Next one. Which one is the function I'm looking at? 2 sine x means the amplitude moved up to 2. So hey, that's my blue function here. So 2 sine x is a blue function. Sine of 2x, that means my period got shortened, so I have to finish it in pi period. So that's my green function here. Okay, now notice in this picture, it's crossing so many times. So this time I am telling you a specific interval. I only want to look from 0 to pi. So if I go from 0 to pi, it is simply this piece right here, from 0 to pi, okay? All right, so now I can write my integral. My area is going to look from 0 to pi. In the region I'm looking at, blue is on top, green is on the bottom. So blue function minus green function. All right, so blue function was 2 sine x. Green function was sine of 2x, okay? So again, make sure you know your tricks to take these integrals. All right, ready to take my antiderivative. The antiderivative of sine x is negative cosine x, so the coefficient 2 stays there. So negative 2 cosine x minus sine 2x, that's cosine 2x. But don't forget to take the 2 out as a coefficient, reciprocal that because we're taking the antiderivative. And then you evaluate 0 to pi. Because we're dealing with cosine now, watch out for your 0, okay? So we have negative 2 cosine of pi minus 1/2 cosine of pi again, or 2 pi actually. Doesn't matter, have the same result anyway. Well, actually, no, it doesn't have the same result. Sorry about that. Okay, and then minus negative 2 cosine of 0 minus 1/2 cosine of 0, because 2 times 0 is still 0. Okay, all right, so I get negative 2 cosine of pi is negative 1 minus 1/2 cosine of 2 pi is 1. And then distribute minus, so plus 2 cosine of 0 is 1 plus 1/2 cosine of 0 is 1. So I get a positive 2 minus 1/2 plus 2 plus 1/2. I actually get a very nice answer of 4. Right when I say start expecting ugly answers, sometimes a surprise comes along and you have a very nice answer. Okay? All right, again, key point is to remind yourself, I call this a mantra because you're going to say this over and over again. You are looking for top minus bottom and right minus left. If it is a top minus bottom function, so again, write yourself a note. If it's top minus bottom, it's going to be a dx problem. Your variables are going to be in terms of x. Your equation's y equal, and your variables are all in terms of x, so you're looking at the x-axis for your interval. If it's right minus left, this is going to be a dy problem. That means your equation is written as x equals something, something y, and your interval is going to be on the y-axis as a range, and then you're going to look at the y values to create your interval. Okay? All right, guys, that's it.